So we have been studying the rule of symmetry in quantum mechanics, rather the rule of symmetry operations. Operate when you identify certain operators which can generate functions uh, which can be symmetric in their corresponding representation. So here, once we not only have translations, we can have rotations, we can have boosts, we can have many things. So in the simplest case, how can we understand space translation, and the thing is that space translations and symmetry sort of operations and how we identify operators. So for example, so if there is a spatial translation, so modulo, for example, that laws of nature should be invariant under some translation, spatial translation or translation invariance. We just identify them. So if, for example, if we shift our coordinate system, for example, so expectation value of particle with coordinate xn. So n may label the individual particles. Individual particles. So it's xn is transformed into xn plus a. So where a is arbitrary 3 vector. So there must exist a unitary operator. For example, the property of U is unitary operator is U dagger U is I, or U inverse U dagger is equal to U inverse, or U operating on something and U inverse or U dagger is. So if you have an operator operating on the same this thing, so if you operate it on this in some translation via this A vector, so that unitary operator should leave the things before and after the operation unchanged in terms of translation, space translation. So it can be identified if you want to identify them in terms of unitary operator, ux, so x of n, u of e. So because u inverse u, it's a unitary operator, it will xn. So after this thing, it should be equivalent to xn. Sorry, xn plus e. So before the unitarity as a property should not differentiate the state of the particle, state of this thing, expectation of value of the particle before and after this A. So now if we want to if we yesterday we tried to define this unitary operator and we defined it in terms of ut, if you remember, we defined it as 1 plus, we defined it as 1 plus epsilon t plus o epsilon square. So T is some epsilon dependent operator, and epsilon is arbitrary infinitesimal number. So there can be higher order terms to it. So you can define unitary operator this thing. Now if you want to make this identification with this, so we can say, we can write a Hermitian operator. So instead of T, we can write it, identify it as minus P by H in place of A, such that UA can be defined as 1 minus iota P dot A by H plus 4 times A square. So this is how we have defined. So the condition requires that for an infinitesimal 3 vector, or infinitesimal. So now we can, if we want to have this condition, this condition, if it's one, this is two. The condition one can be represents for infinitesimal three vector. If you write it in terms of commutator, P dot A, vis-a-vis this xn should be some constant or translational invariance. So if you want to again, so if you want to again introduce it, we want to write it in terms of elementary quantum of action, the commutator and this A, the displacement, and this xn is the original expectation value. So the commutator, if it's so if you want to replace it in terms of, so we can write it as xni pj is iota h. So we can write it in terms of some Kronecker, some delta function. Therefore, ij is 1 or I naught equal to j, it may turn out to be 0. So this commutation arises, relation arises because we express the generator of the special functions, special translations in terms of unit mass velocity. So what we can say is this P has the same the way we have introduced P instead of T. This is Hermitian operator. Is the same commutation as if we are commuting with the coordinate of the particle. So you can just interpret this P as something as its momentum of particle, such that the momentum takes the form and this thing, such that so momentum existing on this spatial coordinate, it will give mxx. So it's commutator of x with x, that will give 0. So you can write it Pn xn with 0 for n not equivalent to n. For n equivalent to n, it may not be 0. For this odd values, for values where n is not equivalent to n, it's 0. And if we now have two indices, ni and pij, so we'll have delta ij and delta kn, something like that. So you can have xni pmj, so we can have ih delta ij delta n. Yes. So of course the individual momentum operators Pn are not the generators of symmetry of nature. So it's a general statement. Of course, individual momentum operators, usually they may not be the generators of the symmetries of nature individually. Now question is that a translation may be followed by a translation by vector B. That's it. So you can have, just like we have U inverse U is equal to 1, so you can have a translation acting on A and translation acting on B, or vice versa. You start with B and then come to A. So there can be a particular vector, so that we can say that UA into UB, we can be written as UB into UA. Such that again, if we want to say the AI, BJ are the components of the momentum that commute with each other. So I and J commute, odd will commutes, in may not commute. So by this thing, so PI, PJ will come out to be 0. So now we are going to use the yesterday's commutation relation. If you remember, we have defined in this after we defined this operator. We could also write it in terms of some function like this, which is going to theta t by n, which is periodically go to recur, and for a certain value, you can write it as exponential of iota theta t. T is the operator here, but instead of t, we have p now. So if you use the same logic here, now at the end, ua, if you want to write it in terms of this, so we can write it as minus iota p dot e by h. Here it's n, so it's p by h here. So it's the unitary operator in terms of this momentum, has some symmetric properties, can be written like this. So if you write it like this, so this is a very simple example of derivation of Commutation relation from the structure of transformation group. That's it. So the question is that your commutation relations of translation group, how the transform, the way I said, when theta goes to, there's an operation commuting thing, theta goes to some operation by an exchange of angle theta, the inverse operation minus theta will flip it back to original state, the operation and the inverse operation. So here there may be rotations associated with these momentum operators. So it may be on one axis or two axes, and depending upon the transformation groups or effect of two rotations around two different axes. So the thing, it may become more complicated. Sometimes they may commute or they may not commute. So the components or the generators of components or of the generators of the rotation by this thing, but generators of rotation, angular momentum vector do not commute with each other. So if phi naught is a one particle state with a different position, so now we are going to come back to how different eigenvector corresponds to eigenstate corresponds to a different eigenstate. So if using that thing, such that if phi naught is one particle state with definite position at the origin, that's eigenstate of position operator x with eigenvalue 0, then according to equation, this first equation, if you remember, first equation, u inverse a x of n u of a is x. So using this equation, first equation, so we can form a state such that we can form a state what? So it's u of x phi naught. So its eigenvalue 0. So it's a definite value, a correspondence of eigenstate at the origin having a definite correspondence. Or we normally write it in terms of x phi x is equal to x phi of x. And from this equation, from one was this equation, the other was this equation, xmj p ij mj equal to iota h delta ig delta n. So for two vectors So you can have from this, you can, if you want to have momentum J with eigenvector x, so you can write it as momentum operator in terms of derivative of this thing. You can write this Pj in terms of this phi x. And if you want to write the scalar product, if you want to write the scalar product of this state, scalar product of this state, scalar product of this state, and then psi of p into phi of x can be written as exponential of psi p and psi 0. Psi 0 is the state at origin, which corresponds to some definite state. Now, if we want to normalize it, psi p phi x can be written as, so just do this normalization yourself and square of this. How we normalize this function? So I will it. So it will come out to be minus 3 by 2 exponential of minus root of 3 dot x by h. So the complex conjugate gives the usual plane wave formula for the. So now we are going to take its complex conjugate of this. Can be written as so complex conjugate means this minus will be for this will be plus, this will be plus, this will be minus. This is phi p phi, so we have flipped it. So fine. And normalization by virtue of this phi satisfy the normalization condition. Again, remember the normalization condition can be phi x prime, phi x will give us three-dimensional, it will be x prime minus x prime. So if you remember when we wrote the, if we see it, the part, the class to the previous class, how we basically describe continuum space states, and how we had a Fourier analysis and the representation of those continuum states. So here we are going to use that thing, that we can write this relation. So if you write this thing, inner product of phi p prime with phi p. So here it's x prime with x p. So we can write it as psi p star psi p, so x. So it will be basically d3 x 2 by h minus 3 exponential of, so again it will be psi p. So it will be iota, will get it back, p minus p prime minus p prime x by h. So if you remember the Fourier analysis, we can write this thing. We can write delta of x minus x prime is 1 by iota k x minus x prime. So now the k is p by h. So again, so this commutation relation between phi and phi prime can be written as, so it was this thing, and phi of zeta prime, phi of zeta prime was basically delta zeta minus zeta prime. So this phi p phi prime can be written as phi p prime into phi p. So the product of these things will be delta 3p minus p prime, which is the required equation. Now again, for example, in some external environments, Hamiltonian may not be invariant under all translations, but only under a, so it's not only Hamiltonian, Lagrangian may not be or Hamiltonian may not be invariant under some translation, but in subgroup of those translations. Just like we have in a finite dimensional vector space, so it's not the correspondence. So the relationship, the map will exist between the subspaces, not the total space of a given dimensions. So a certain identity may hold in a given subspace rather than the whole space spanning that finite dimensional space or Hilbert space or vector space. In the same way, this translation or rotation or invariance properties may not hold for an entire group but a subgroup of translation group. So for a three-dimensional crystal, so we have some bit of intuition of geometry, solid geometry, or some intuition of crystallography or solid state physics, how we identify them and how we can just classify them, and here also. So what we are saying that Hamiltonian, which is invariant under spatial translation, where R is 1, 2, 3, and LR are independent translation vectors, not their components. So for example, in a cubic lattice, so if you take a sodium chloride, LR are the orthogonal vectors of equal length, but in general they do not need to be either orthogonal or equal. So for a particular sodium chloride crystal, they need not to be orthogonal or of the same length. For cubic crystals, you can just take it that way. But if it's sodium crystal, it may not be symmetric in the exact sense. So the translations may not exactly follow that sense. So now what we are going to take, for example, assuming that no, then we can take psi of x r x plus lr with r going to 1, 2, 3. So the solution having the same energy. Assuming that there is no degeneration, the normalization of wave function to be a phase vector, we can have a function which has this. It will repeat after this psi of x, where theta are right angles. So in the language of group theory, the wave functions provides a one-dimensional representation of group of translations that consists of all fundamental these translations. And without a loss of generality, we can say that 0 is less than theta or is less than 2 pi. So it will lie between the value of theta, which is the translational vector. It may have a minimum to maximum. So it can just have this thing. From it may have a 0 angle and maximum it can be 2 pi. That's it. And we can also define a wave vector q by the condition that q dot lr is equal to theta r. So it's the point is that how we can say that we can have this translational invariance property for a given Hamiltonian, which can exist in space. And the more thing is when you study a Kronig-Pennine model in solid state physics or block waves, where we say that psi of x will be equal to iota k dot x into phi of x, and phi of x plus L will be equal to phi of x. So it will be sort of the thing when you start at the first equation. So it may sort of have mimic this thing. The way we define or unitary operators for a translation axis and some translation axis which is model some constant or whatever that is. So you can have this thing. this identification, use identification. So there R is or LR, where R is 1, 2, 3. So which in literature are also called block waves. And if we have a Schrodinger equation for it, Hamiltonian, the evolution of Hamiltonian wave function. So left hand side, it's psi x, and if it's this some periodicity is attached to it, so you can say you can also have phi of x is equal to, if it's phi x satisfies q dependent equation. It's q dependent equation. It is psi. Psi is the and this is Schrodinger equation. This is q dependent equation with the periodic boundary conditions. And where q dot LR is less than 2 pi. So you can, the point is that we can in quantum mechanical understanding of things, how we can identify these parameters here so that we can have these space translations possible. And we have a particular operator which comes, we have a particular operator correspondence, the way we wrote yesterday. This O of E square. So we have this P operator. How we define an operator which will it's a sort of symmetry operator which is going to repeat periodically. Generate that via that symmetry can generate that function so that symmetry here is the translational symmetry, and we can say that we can work out in some these examples of solid state physics like them here. So we start today. The next thing is we are going to have time translation. The way we had space translations, so we also can have a function may be symmetric in time, but it will take more time, so we'll postpone it for next class.